Mhm. So let's take another question.
Another question under the at rest. Alright, so okay, so we have a retaining wall of height 5 meters. Then we have the following parameters as usual. Then we are being told the soil is restrained from movement. So since we know that the soil is restrained from movement, then we are talking about active an at rest condition. An at rest condition. So in here we have a water table. In the first example we saw there was no water table. So know that this is also an at rest condition. So now we have to find K naught, we have to find our force, and we have to find our point of action. Right. So let's start. So just as we said, the first step is to find your A naught. And in this question too. So now by in this question, we have our over consolidated ratio. We have an over consolidated ratio. Well, let's say we have OCR of 2, okay? OCR of 2. So now our first thing is to find our K naught. So since we have our OCR and an angle of friction, which is the phi, we are simply going to use the that's the general formula. We say that we have 1 minus sine phi multiplying the OCR to the power sine phi. So we have 1 minus, what was our phi? 32. Then our OCR is 2. Our OCR is 2, and again to the power sine 32. Computing this, we have 0.6787. So we've succeeded in finding our K naught. Now the next thing is to find for our force, right? But before we can find our force, just as I said, in finding the force, you need a pressure diagram. So finding the area of the pressure diagram gives you the lateral force. So now before that, we will need to, and in drawing the pressure diagram, you need to find your pressure with respect to depth. So you find the pressure at the respective depth. So now we have a retaining wall of height 5 meters. And since again this is at rest, we have our general formula for at rest condition for the pressure to be what gamma prime z K naught plus gamma w z K naught, where this is for water, this is also for water. So let's say that at z equals 0 meters, right? Our lateral stress is equal to what's our gamma? Our gamma, so at z equals 0, we are over here, right? 0 meters. What's the gamma over there? We have 17. It's a distance of 0. What's our K naught? 0.6787 plus gamma of water being 10. Then, okay. So again, we are going to check at this point, which is z equals 0. Do we have any water column above it? We don't. So meaning that the whole thing goes towards 0. Then we have our gamma naught, our sigma naught at a z of 0 meters to be equal to what? 0. Then we proceed by at z equals. So let's see, the whole distance is 5, but we have the whole distance, we have 5 meters here, we have 2 meters here. Let's make it this way. Okay. Yeah. So z z equals 5 meters, what do we have? We have our lateral stress to be 17 multiplying what? 5. Then our K naught 0.6787, right? After this, okay, so we've already, so now again at this point, though there is, you can see that the water table diagram is here, we consider the water column above it. So at this point, there is no water column above it. So again, this whole thing goes towards 0. Then we have our lateral stress at a distance of 5 meters to be 57.686895, and your unit is very important, kilopascal or kilonewton per meter squared. Now again, at z equals 7 meters, sorry, it's an h, not z. At z equals 7 meters, our lateral stress becomes what? So now over here, note something. We are finding our lateral stress at this point. So in situations where you have a water table, you do your computations with the first part of the computation deals with the fact that there is no water. Then the second part deals with the fact that there is a presence of water only. So what you do over here is that at z equals 7 meters, z equals 7 meters deals with from 5, everything over here, right? But you realize that from here to here, from here to here, there is no water, right? The water only starts from here to here. So what you do is you find your, so again with the formula gamma z k naught, we have 17 by what? 17 by 5, right? 17 by 5 plus the gamma over here, which is 19. But this gamma, you assume you subtract the gamma of water from it because we want to deal with the fact that there is no water. Okay, so 19 by 10, then you multiply this by the distance. So since we are here, so we've already done for this part. So this part is what? 2. So this is for the gamma z, right? This is for the gamma z. Then our next thing is our K naught. So what our K naught? Our K naught is 0.6787 plus this aspect. Is there water? We are here. Is there a column of water above it? Yes, there is a column of water above it. So our gamma of water is what? 10. What's our Z? Our Z is 2. Then what's our K naught of water? So just as we said, our K naught of water is 1. So computing this, we have 89.9061 kilopascal. Now the next thing is to draw your pressure diagram. And no, take note of the parameters. The next thing is we should draw pressure our pressure diagram. Now, so let's assume so this is our retaining wall, just as we had initially. Our retaining wall, just as we had initially. Then, so from here, here is 5 meters, here is 2 meters from the question. So at z equals 0 meters, what did we get? We had our pressure over there to be 0. Now at z equals 5 meters, we had our pressure to be 57.6895. So let's say here. Then at z equals 7 meters, we had 89.90. So let's say here. So we're drawing this to this, then we're drawing this to this. Right. So here is the 57.6895. Then we have 89.9061. So this is your pressure diagram. The next thing is to find the force. So you know that in finding the force, you need to find the area of the pressure diagram. So we can put this into simple shapes so that we're able to find. So we can say here is A1, A2, and A3. So from here to here is 57.6895. So again, so here it is 95. The whole thing is 89.9061. And from here to here is 67, meaning that from here to here will be what 30.2166. Don't forget your units that they are in, which is the summation of the areas. So A1 is equal to half. So this A1 half is a triangle. So half times the base 57.6895 times the height, which is 5. And this will be giving us 144.22375 kilo Newton per meter, right? A2 is simply a rectangle, so the length times the breadth. So 57.6895 times 2. And this will be giving us 115.379 kilonewton per meter. Then we find A3, which is a triangle, so half times the base, 30.2166 times the height, which is also 2. And this still gives us 30.2166 kilonewton per meter. Now, P naught is simply, which is the force we are finding, simply A1 plus A2 plus A3, the summation. So you add this to this to this, then you get your P naught. And in doing that, we have 289.819 kilonewton per meter. I've already explained why it's kilonewton per meter. Now, the next thing we're supposed to do, we're supposed to determine the point of action of the lateral force with respect to the base of the wall. So let's come back to our diagram. Now, the force in A1 will act, let me call this P1. Then I call this P2. Okay, so let's make it. So this, you know that this A1, this A2, and this A3. Now our P naught, which is the lateral force, will act at a, let's say here's P naught, at a distance of X from the base. And this is the point of application. That's what we are finding for. So in doing this, we take moment about the base, moment about the base. So P naught, we take a moment to realize that this is the moment arm for P naught. So P naught will take a moment of what X. So we have P naught by X, right? They should be equal to A1, which is also acting in this direction, right? We'll take a moment about a distance from here to here and from here to here. So the moment arm for A1 is just going to be the centroid of A1, right? Plus the remaining distance to this side. So we have A1, this is simply a triangle. And I've already told you that this is the longest part. This is the longest part. So here is 2/3 of the height. This is the shortest part. So this is 1/3 of the height. So we have 1/3 of the height over there, which is 5. But when we take 1/3 of the height, we end up at this point. But we end up at this point, but we're taking moment about this base. So we add the remaining distance to get here. So plus 2. That's for A1. Then now we have A2. A2 also take a moment. This is the moment about this point. And since it's a rectangle, it's simply half of the distance. So half of 2 plus A3. This A3, which is also taking a moment. This is a triangle. So again, 1/3 of 2. You already know what A1 is. You've calculated for A1, A2, and A3. So you substitute that inside. And you know what P naught is as well. You've already calculated for P naught. So now the only parameter unknown is your X. So you substitute that, then in complete be having 289.819x being 664.3438. So our X is simply 664.3438 all over 289.819. Then we have 2.29 meters. 2.29 meters. So meaning that our force, which our lateral force, P naught, will act at a distance of 2.29 meters from the base of the retaining wall. From the base of the retaining wall. So this is how complex the at rest condition can be. So taking an example where we have where there is no pore water pressure, and another example where there is pore water pressure. Now let's consider cases for the passive. Let's consider cases for the passive state. Again, if as I put out the question, let me say this. Before, in order for you to know whether it's an active, passive, or at rest, it's either the question gives you a clue or you are being told directly. So for at rest, you'll be hearing something like restraint from movement or a rigid retaining wall. For passive, you'll be hearing something like the retaining wall moves into the soil, or you'll be seeing an anchor, just like I drew in so a tie and an anchor, just like I drew in the first one. Then, or you'll be hearing something like the retaining wall moves away from the soil, and that's going to give you an active case, right? So under Rankine's passive and Rankine's active, we are starting with the Rankine's passive, an example. So we have a simple retaining wall this way. So the moment you see this anchor, then you should know that we are dealing with a passive state. We've been given our phi. First of all, let me start with a cohesionless state. A cohesionless state. So this is our question. Then we've been asked to find, we've been asked to find the force as well as the point of action of the force. The force, the height of the retaining wall is 6 meters. You have to find the force as well as the point of action of the force. So in doing this, so let's start. Again, we are going through our 5 procedures. So we find our Kp, which is simply 1 plus sine phi over 1 minus sine phi. So we have 1 plus sine 28 over 1 minus sine 28. In doing this, we have our Kp to be 2.7698. The next thing is to find the lateral force at the respective distance. And we know that the lateral force, the formula is given by gamma v Kp plus what? 2c prime root of what? Kp. Now, the next thing is that we are to find for, so we are going to find the forces at each distance. So again, at z equals, so you now know why I said you just go through 5 basic steps. So again, at z equals 0 meters, then we put our formula, right? What's our gamma? 19. What's our z? 0. So again, over here too, let me add the column of water. So plus gamma w kp, right? Gamma w z kp of what? Of water for a generalized case, right? So 19 by 0, what's our kp? 2.7698 plus 2, right? What's c? So this is 0. So 0 root of 2.7698 plus, you realize that there is no column of water above it, so plus 0. Then computing this, we have what? 0, 0, right? We have 0, right? Or don't, yes. So this is a case for a cohesionless soil. So we have 0. Now, then we move on to finding, so this is a passive state. There's a passive, cohesionless passive. So the next thing is this was at 0 meters. So now let's find for at 6 meters, right? At v equals 6 meters. So at v equals 6 meters, we have what? 19 by 19 by 6. 19 by 6. 2.798 plus 2 again. The soil is cohesionless. So 2.7698. Again, over here, we do not have any column of water over here. So again, plus 0. Then we have our lateral stress in the passive form to be 315.7572 kilopascal. 72 kilopascal. Now, the next thing you have to do after finding your pressure is to draw the pressure diagram, right? So again, this is our retaining wall. What's the pressure at Z equals 0? It was 0. And the pressure at Z equals 6. So we have this where we have 315.7572 kilopascal. So in finding P dot, we find the area half times 315.7572 times the height, which is what? 6. So by 6. Then we find our area. So we have half in computing this, what do you get? Like 315.7572 by 6. That's the area being 947.2716 kilonewton per meter. Then since this is simply a simple triangle, if you want to find the point of action, it's simply 1/3 of what? The height. So we have 1/3 of 6, and that will be giving you 2 meters. So this is so note that this is a simple case where there is no water table and also for cohesionless soil. Either you are hearing cohesionless means B equals 0, or you can also hear granular soil, meaning that C equals what? 0. So let's take another question under passive, where there is, again, let's say for cohesionless soil with the presence of a water table. Okay. Cohesionless soil where there is a water table. So let's take a very simple question again. All right. So let's take this question. So for cohesion, so just follow the same approach, but I want to solve this. So again, this thing we are going to solve the same. We are just going through the same aspect and calculate for whatever I want to calculate. So the first thing, find your KP, right? When you find your KP, you have what? 1 plus sine phi over 1 minus sine phi. So we have 1 plus sine 28 over 1 minus sine 28, right? And this will be giving you 2.7698 again. Then let's find our stresses, right? What's our formula? Our formula is gamma z kp plus 2c root of kp. So at z equals 0 meters, what do we have? At z equals 0, we have, just put it inside. This goes to 0, right? So this whole thing goes to 0. But since we have a c, so let me just go ahead. And so 19 by 0 multiplying 2.7698, right? Plus 2, what's our c? 22 root of 2.7698. And this will be giving us what? 73.2280 kilopascal. Now, the next thing at V equals, so the height of the retaining wall is also 6, okay? So at D equals 6 meters, we have our lateral stress to be 19 again by 6 multiplying 2.7698. So over here, so don't forget that we can have plus gamma W whatever, but I didn't write it because you can't see any column of water over there. So that whole aspect goes to there. Right. So 19 by 6 by the this yes plus 222 square root of what 2.7698. Computing this, what do we have? We have 388.9852 kilopascal. The next thing is to draw a pressure diagram. So if this is my retaining wall, right, my retaining wall, at depth equals 0 meters, what did I get? I didn't get 0. I had 73.2280. So that will be on this line over here, 73.2280. Then at depth equals 6 meters, what did we have? We have 38. So that will be, so if this is somewhere here, that will be somewhere here. So we join this line to make it. So we have this shape where this side is 388.9852. So this becomes 82. The distance from this point to this point is 73.2280, which is the same as over here, right? So if I want to get this distance, I can subtract this from this. Then I have 315.7572 over here, then 73.2280. So again, E naught is simply A1 plus A2. A1 plus A2. What's A1? Half times. So A1 is simply half times the base. What's the base of the first one? Sorry, A1 is the rectangle, right? So it's simply the length times the breadth. So 73.2280 by the breadth, which is 6. So we have a distance of 6 over here. Then what do we get for A1? 439.368 kilonewton per meter. Then A2 is simply half times the base. What's the base? 315.7572 times again 6. And what do we have? We have 947. We have 947.27. So if you want to find P naught, P naught is simply P naught is simply A1 plus A2, 9.368 plus 947.2715. And this will be giving us 1386.6395 kilonewton per meter for the force. And again, if you want to find the point of action, this was the shape we were having. We are having this shape. We're having this shape, right, at a distance of 6. So this is our A1, this is our A2. Then our P will act somewhere here at a distance of what? X. So we have P naught, PP. PP, since we are doing with passive, PP, since we are doing with passive, PP. So PP times X should be equal to A1. A1 was what? 439.368 times the centroid to the base. So since A1 is simply a rectangle, we have half of 6 plus A2. A2 is also A2 is also a rectangle, a triangle. So A2 is, we have the area 9.2715, right? By 1/3 of 6. Then over here we have 3212.647 pp of x. You know what pp is as well. pp is 1386.6395. So you simplifying for x and you're getting 2.32 meters by simply dividing both sides by 1386.6695. So this is also another case under Rankine's passive where we have
a cohesive soil. So we're giving C and phi. So you can also try an example where you've been given C, you've been given so this case we solved had no water table, right? So let's solve for a case where there is water table, just like what we did in the past. In a case where there is a water table, we know what you have to do already. You find Kp, 1 plus sine phi, 1 minus 1 plus sine phi, 1 minus sine phi, 132, 1 minus sine 32. What do we have? 0.2546. Now find your what formula do you use? Gamma z Kp plus 2c square root of Kp plus gamma w z Kpw. So at z equals 0 meters, we have our lateral pressure to be what? Automatically, you know that you get what? You get 0 because z here is 0, e is also 0. We don't have any water column over here, so we get 0, right? Any water column over here, so we get 0, right? Then the next